Welcome, ladies and gentlemen of physical science. You are at home, most likely, working on this free body diagram simulation online. This can be a tiny bit frustrating, so I decided to make this instructional video to help you out with it. Free body diagrams were introduced this last week to show you how forces act on an object. There are 10 situations here. I'm going to walk you through multiple of these to show you how this works. This is a skill you just have to put some time in, you have to struggle with, and then the light bulb will start to go on. First of all, when you click on one of these situations, if you close down this window, then it opens it back up. Situation one will not be the same for you. It shuffles. So once you start this process, stick with it, okay? You're going to get a story here, and this is our free body diagram right here. This box represents whatever we're talking about. In this case, an elevator, okay? There are no forces now. What it says is the cabin of a small freight elevator is secured to a motor by a cable, and it's moving upward at a constant speed. There's no contact between the cabin and the elevator shaft, so there's nothing touching the outside of the elevator shaft, just this cable on the top, okay? And it says we get to ignore air resistance. What does all of that mean? There's a ton of information in there. The first thing I'm going to do is decide what force and in which direction is currently acting on this elevator. Well, if there's a cable pulling the elevator up, then there's got to be a force on the top of this box moving in an upward direction. So I come down here to the left side of the screen, and I click on the up button. The up button says, and it's not showing me everything right now. What in the world is going on here? The up button, sorry, that's a little bit smaller, but that's the only way I can show you this. This says that now I have to choose which force is up. Well, here's a new one. Anything that is a cable or a rope or a chain is tension. So I click on tension, and it's in an upward direction. Force, tension. Now what I can do is click on the arrow to make it longer or shorter, depending on if I want it to be bigger or smaller than any other forces I attach to it. Okay? Now, here's the other thing. This elevator is on Earth, so there's got to be the force of gravity down. So I click down, I choose gravity, and now it gives me an arrow that's the same length as the tension. Now we can make it bigger or smaller, but there's a clue. In here it says that the elevator is moving upward with a constant speed. The only way for this elevator to be moving at a constant speed with no acceleration is if it has a net force of 0. In other words, this tension force up has got to be canceled out by gravity down. So the arrows can both be long or they can both be short, but they have to be the same length. Otherwise, one would be stronger than the other and it would be accelerating. I don't think there's anything else in the story that warrants me putting a force on here. So when I think I've got it, I click on check, and it tells me, congratulations, you're so darn smart. Maybe you should become a science teacher, right? And then I go back to the main menu, and you'll notice that there is a little star next to situation 1. Well, you've seen the elevator one, okay? So you can use that information in this video to do that. Now we'll move on to situation 2 and read the next one. There is a downward moving skydiver, but he's falling at a constant speed. So every time I see that, that means every time I see constant speed, I want you to think net force of 0. That means that all of the forces have to cancel out. The skydiver can still be moving, but he must be moving at a constant speed. So what do I know? Well, I know on planet Earth there's going to be this downward force of gravity. So what in the world could be working in an upward direction that would cancel out gravity? Because I need this skydiver to be falling at a constant speed. So something moving in the upward direction. And what could it be? What could it be? Well, it's not a normal force because he's not touching a solid object, right? I'm going to go with air resistance. The skydiver is falling through the air, and air has to be the same strength as gravity. Now watch what happens. Let's say I make my air larger than the force of gravity, and I click check. It'll tell me, sorry, it won't tell me what's wrong with it, but it will tell me that something is wrong. And so I can go back and make a change. When I feel confident, I can click it again and check it, and it will tell me if I'm right or wrong. So there you go. There's the skydiver one. I want to do one that has some horizontal forces as well. So let's try situation 3. A sledder has reached the bottom of a hill and is coasting to the right Okay. On this loosely packed snow. So if the sledder's moving to the right, what do we know? Well, we know that there's gravity. Can almost always start with that one. But the sledder is not falling through the snow, so there's got to be something pushing up on the sledder. And in this case, that would be the normal force because the sledder is in contact with the ground. All right? Now here's the tricky thing. I have students that want to say, well, the sledder's moving to the right, so there's got to be a force to the right. Actually, no, there doesn't need to be. There's nothing in the story that says the sledder's being pushed. Gravity got them moving down the hill, and then when they're coasting at the bottom, there's no push or pull that's making them move that direction. So there's actually no force to the right or to the left. Oh, it's not correct. What's wrong? Something is missing. The sledder's reached the bottom of the hill and is coasting to the right while slowing down. What would cause a sledder that's moving to the right to slow down? There's got to be something in the leftward direction, and it's going to be friction. Friction always works in the opposite direction of the motion, and so that would explain why they're slowing down, and yes, that is correct. Okay, let's do one more together. Situation 4. A football, originally kicked at a 40-degree angle to the horizontal, is at the peak of its trajectory, and we get to ignore air resistance. I love this one because students like to make it seem so complex. The football's in the air. It's already been kicked. My foot is no longer in contact with it. We're getting to ignore air. There's only one thing acting on this football, and that, ladies and gentlemen, is gravity. And that's it. Please be prepared to get a bunch of these wrong. All right? Don't get frustrated with it. I don't expect you to get all 12 stars right away. But what I would like you to do is get 12 stars eventually and send me a screenshot that you've done that. In order to do that, you got to try these, click on a whole bunch of stuff, and get a bunch of stuff wrong. And then I need you to write down which of these you're having difficulty with. Don't write situation 5. I had trouble with situation 5 because my situation 5 won't be yours. If you close down the window and open it back up, your situation 5 won't even be the same. So write down, I had trouble with the hockey puck one, or I had trouble with the sliding book across the table one. And then we can help you find as many answers as possible. Please don't spend more than 30 minutes working through these, whether you get 12 stars or not. Okay? If you want to put in more time, you can. But I want you to focus on 30 minutes of time working through these free body diagrams. Good luck.